Hi guys, I'm not here today, but I thought you guys could go ahead and do this on your own with a little bit of help, so I'm going to try and get you started. We're going to talk about section 7.1 exponential models, and the first thing we're going to learn how to do is how to graph them. And basically the easiest way is you're going to make a table. So what we're going to do is graph a function that looks like y is equal to some a times b to the x. In exponential models, x is now going to be in the exponent, all right? Typically, we've done things like linear functions or quadratics or polynomials, and in each of those cases, x was some number we were raising to a power. In the case of linear functions, we were raising it to the first power. In the case of quadratics, we were raising it to the second power. Polynomials, we were raising it to different powers. But in this case, x is the power that we're going to be raising to. And so these have a characteristic shape, and we're going to draw one out as we make the table. So let's do y is equal to, let's just start with a simple one. Let's just say y is equal to 2 to the x power. All right. We're going to graph this function. I'm going to make a table of values. We get to choose the x's that we plug into our table. So let's choose, let's start with 0. Remember, anything raised to the 0 power, in this case we'll have y is equal to 2 to the 0 power. Anything raised to the 0 power is 1, so we just get 1 here. So when we plug in 0 for our x, we get 1 for our y. Let's do the next one. Maybe we'll try y is equal to 2 to the first power. Of course, we know 2 to the first power is 2. So when you plug in 1, you get 2. Let's do the next one. What do you think? 3? Or 2 maybe? 2 to the second power. 2 to the second power is 4. So when we plug in 2, we get 4. Let's go one more in that direction. Y is equal to 2 to the third this time, and 2 to the third is 8. So when we plug in 3, we get 8. Now each of these are points, and we can plot them. The problem is that we need to put in some negative values as well. So let's try a -1. Y is equal to 2 to the -1. Hopefully remember when you put in negative exponents, remember it's going to kind of flip it upside down. So 2 to the -1 is equal to 1/2. So we'll write that in there. Plug in -2. Y is equal to 2 to the -2. 2 to the -2 is like 1 over 2 squared, which is 1/4. And we'll go one more. We'll plug in -3. Y is equal to 2 to the -3 would be 1 over 8, since 2 to the third is 8. And so when we plug in -3, we get 1/8. So let's plot some of these points here. The point 0, 1 lives here on my graph. The point 1, 2, we'll go over 1 and up 2, lives there. The point 2, 4, oops, did I count right? 1, 2, 3, 4, lives there. And finally the point 3, 8, way up there. Now go in the other direction. When we have -1, it was at 1/2. When x was -2, y was 1/4. When x was -3, y was 1/8. And I think you get a pretty good idea what's happening here. We'll connect our dots. And this shape right here is the exponential growth shape. All right, it starts off and is what's called asymptotic to the x-axis. That means that it gets very, very close to the x-axis, but it never actually touches nor crosses it. It just gets closer and closer and closer as you go in the negative x direction. As we go in the positive x direction, the y values just get bigger and bigger. It grows very fast. exponential functions model real-world situations like what happens to populations. If we had started with 2 rabbits, after a few months or whatever, we end up with more rabbits. 4, then 8, then 16. It's going to grow really fast. The same thing hopefully happens with money when you invest. You invest your money into a bank account and they pay you interest. That as well is going to be exponential growth. It just doesn't grow as fast, although we wish it did. This is called exponential growth. There is something called exponential decay as well. When you go to get, like suppose you got sick and they thought you had strep throat, you might go to the doctor and the doctor would swab around in your throat and try to grow cultures to tell whether or not they were cultures, streptococcus virus or bacteria rather. And if it was, they can look at it under a microscope and identify it because it has a certain look. But they have to wait a couple of days for it to actually grow colony-wise to a large enough population that they can see it under their microscope. So they exponentially grow. Now what the doctor will do if you have strep is he'll give you antibiotics. And those antibiotics kill the bacteria. And they do it exponentially, but this time exponentially decay. So you have all this bacteria that's in your system, and it just keeps growing and growing, and you feel worse and worse. But when the doctor gives you antibiotics, then the opposite happens as the antibiotics start to kill off the bacteria, and they do it in an exponential fashion. So like the first day you're not going to feel real great, second day you start feeling a little bit better, next day a lot better, and the next day a lot better, and pretty soon you feel just fine. Because it exponentially decays, or the bacteria exponentially decays in your system, and you're left with hardly any after a short period of time. All right. If you want to follow along, by the way, I'm on page 435, and they're showing you a picture of exponential growth, which again looks like this. There's also exponential decay. Exponential decay has a characteristic shape where it goes in the opposite direction. So if the curve had gone this direction instead, okay, this is going to look like exponential decay. Now some of you hopefully are saying, well, how do I know when it's going to be growth and when it's going to be decay? The typical exponential function looks like this. Y is equal to some a times, oops, I put an x. X is going in the exponent. Remember, they're exponential. A times b to the x, okay? Now we could move these things around and do transformations like we've done in the past, but I think for us we'll just stick with the tables for right now. B is the indicator to tell you whether or not it's going to be growth or decay. And you're actually going to get problems in your homework that say, hey, is this exponential growth or is it exponential decay? And it is as simple as this. If B is greater than 1, right, positive 1, so numbers like 2 or 3 or 4, then it's called growth. Okay? If B is bigger than 1, it's growth. If it's a fraction, if it lives between 0 and 1, right? Let's put a B in there. If B lives between 0 and 1, then it's called decay. So these are numbers like 1/2 or 1/4 or 3/4, a number that lives between 0 and 1, some fraction, okay? If B is a fraction, then it's decay. If B is bigger than 1, it's growth, and that's all there is to it. It's as simple as that. So in your book it has a little example there on page 435. It says, what is this? And it gives us an equation. It says y is equal to 12 times the number 0.95 to the x. What do you think? Should that be growth or should it be decay? Remember, we're just looking at B because it tells us if it's growth or decay. And B, in this case, is 0.95. So I'm going to look up here and say that's between 0 and 1, so this function shows me decay. And its graph would look like this. Alright? That's exponential decay. Second example, y is equal to 0.25 times 2 to the x. What do you think, growth or decay? Once again, look to your b. 2 is our b. It's the thing that's being raised to the x power. 2 is bigger than 1, therefore it's exponential growth. And so this function is going to very much look like this one that we had up here. It's growing. It's exponential growth. So this is the standard form of an exponential function. It can either be exponential growth or it could be exponential decay. The way you tell the difference is you look at b, the number that's being raised to the x power, and if it's bigger than 1, it's growth. If it's less than 1, it's decay. All right? Here's how things work. Let's say that we have a problem in the book that's going to tell us, let's see. Page 436, it says, you're investing $1,000 into a savings account at the end of your 6th grade. The account pays 5% annual interest. How much money would be in the account after 6 years? Here's the way that it works, because some of you may be wondering what this a is we keep writing. We have a times b to the x. If b tells you if it's growth or decay, what is a doing? Well, a is the initial value. If we were looking at rabbit populations and we started with 2 rabbits, then a would be 2. If we're going to do this problem and it says, oh, we put money into an account at the beginning of 6th grade, the amount that we put in is going to be our a. So in this case, if we put $1,000 in, I can write this function by saying y is equal to 1,000. That's our initial value. Okay? So times some b to the x, or in this case t, because we're going to leave it in there for so many years, and we usually call that time, so we'll use t. Here's the deal. It says it pays an annual interest rate of 5%. Well, I can't put 5% here, because as a percentage, 5%, as hopefully you know, is equal to 0.05, okay, as a decimal. And if I used 0.05, that would be exponential decay. And hopefully, when we put $1,000 into our bank account, it grows, it doesn't decay. B is always given by either adding or subtracting the value, the percentage, from 1 or to 1. In this case, because it's exponential growth, our B is going to be 1 plus 0.05. Okay? B is always, when you read these problems, either going to be 1 plus a number or 1 minus a number, and it's up to you to figure out whether the problem is going to be exponential growth or exponential decay. In this case, it's growth, so I added. So, when you work these problems out, you have y is equal to 1,000, our initial value, times 1.05. That's 1 plus 5%, raised to a certain amount of time. And in this particular problem, they said find out after 6 years. So we'll put 6 in for our x or our t. You can just do that in your calculator. Turn mine on. Hopefully you can maybe read this. We're going to do 1,000 times 1.05 raised to the 6th power.